So thank you very much for the invitation. So I am working not so far from here in Chambéry. So there is a strong connection between Turin, Torino, and Chambéry, of course. And okay, I will talk about Markov numbers. And this is interesting because he made this work during his PhD. Okay. And then he shift to Markov chains and so on. So it's interesting to see the link between Markov and number theory. So this is an amazing book about uniqueness conjecture and Markov theorem. So this is a conjecture which are more than 100 years. So this is why it's so interesting. And also there is a lot of topics, in fact, from number theory to combinatorics, perfect matchings, and so on. So we will see many methods, and it's quite interesting. So first of all, we will look at approximation of real numbers. So it's number theory, and then Diophantine equation, and then we jump to more combinatorial or combinatorics or computer science stuff, like a tree of Markov triples. We'll see combinatorics on words, and maybe we will go to these three conjecture of Enier. Okay, we will see this. So here, from the beginning, is about number theory. There is a nice theorem of Dirichlet. So if you have alpha, which is a real, and n is an integer, there exists p over q in the q, and q less or equal to n, such that if you are looking at the distance from alpha to p over q is less than 1 over qn. And in general, we just write this as it's less or equal to 1 over q squared. Okay, so this is really interesting. And if you have an irrational, so there are infinitely many p over q. So in fact, we can approximate an irrational by p over q, in fact, and infinitely many times. Okay, and as you know, we can call algebraic numbers of degree d if the complex number is a root of polynomial with integer coefficients of degree d. And d is the smallest degree, of course. And for example, the square root of 2 is algebraic of degree 2 because it is a solution of x to the power 2 minus 2 equals 0. Okay. So this is simple. And there are also irrationals that are transcendental. And this is the first example from Liouville. You can see that you are putting one position n factorial in the digits here. And this is the first transcendental number. And you can prove that E or P are transcendental also. So now, Liouville's theorem, it's interesting because you can't be too near of an irrational number, in fact. So if alpha is an algebraic of degree d, so you can prove that the distance between alpha and p over q is greater than c over q to the power d. So it's quite nice. And there is a link between a rational approximation and degree of algebraic numbers. But you have the opposite. If you have alpha a real number, and if there are infinitely many p over q at distance less than 1 over q to the power 2 plus epsilon, so alpha is transcendental. So if you are too near an irrational number, so it means that the number is transcendental. Okay, so in fact, you can see that the power is 2 plus epsilon, so you can't improve the exponent. You just have to see at the coefficient near q square when you are making the approximation on 1 over L q square. So we are looking at the L, and we can define the Lagrange spectrum. It's just the sup over all L that satisfy exactly alpha minus p over q in absolute value less than 1 over L q square. Okay, and this is the definition of the Lagrange spectrum. And be careful, we will take the Lagrange spectrum below 3 in order to have a discrete spectrum. Okay, if you are looking at all the values, you have a part which is continuous, and we are just looking at the discrete part of the spectrum. Okay, let's try to investigate this. So in fact, we can put in front of q square square root of 5, and in fact, the value with the Lagrange spectrum of 1 plus square root of 5 divided by 2 is exactly square root of 5. Okay, and in fact, this is the most badly approximated quadratic number, as you know. And in fact, square root of 5 is the first element of your Lagrange spectrum. So you can look at many other elements, and we can use homography. So if you take alpha and beta, you could say that they are cousins if beta is equal to this homographic computation. So it's alpha plus b divided by c alpha plus d. Okay, and of course you have a AD minus BC equal plus 1 or minus 1. And you can prove that the Lagrange number associated with alpha and its cousin is the same. So to go further, you have to take other irrationals, which are neither 1 plus square root of 5 divided by 2, nor a cousin of this. And then you can jump to the other value. And the other value is a square root of 8, exactly. And you can go further. So you have a square root of 221 divided by 5. This is the third value of the Lagrange spectrum. Okay, it's quite difficult to investigate this. This is why we are using other methods linked with continued fractions. And this is one book about continued fraction by Berstel, Love, Rettenauer, and Saviola. And so this is the usual definition of the continued fraction. And in fact, you are able to look at the different values. Here, this is a periodic continued fraction with always 1. Here it's always 2. So always 1 is the first value of the spectrum. Always 2 is the second one. And here you alternate 1, 2, and 1, 2, 1, 2. This is the third element. And then you are able to construct all the continued fraction associated with the Lagrange spectrum. And you have nice properties. Like, for example, there are balance words, in fact. Okay, well. And okay, we can define a set which is Markoff numbers. So the set is 1, 2, 5, and so on. And you have all these Markoff numbers, and you can use the Markoff number in order to describe the Lagrange spectrum. So if you take M, one Markoff number, so the Lagrange spectrum below 3 is exactly square root of 9m squared minus 4 divided by m. And this is interesting because you can see all the Markoff number. We will see how to define this sequence of numbers. And you have many properties. Here, for example, you can see that there is a tree of Markoff numbers, and we will see how to generate it. Okay, let's go. So now we jump to Diophantine equation, and this equation is related to Markoff number. You have x to the power 2 plus y power 2 plus z power 2 equals 3x yz. So this is you have a triple, okay? So of positive integers, and you are able to define, in fact, the Markoff numbers using this equation. For example, you have the first triplet is 1, 1, 1. Okay, you have 3 equals 3. Okay, good. And the second is 1, 1, 2. So you are able to see that 6 equals 6. Very, very nice. But the first triple with all non-repeated values is 1, 2, 5. Okay, you can check it. And in fact, there is a tree structure. If you have, you can put LMR. M is the maximal value of your triplet. Here it's 5, for example, and then it gives birth to 2 other triplets. So you have L, 3LM minus R and M, or M, 3MR minus L and R. So you are able to generate a tree like this. So it's quite nice because you are using, in fact, the Diophantine equation in order to generate all triplets. And the Markoff numbers are exactly the maximum of each triplet. So here you have an infinite tree like this, and you can see that, okay, we can find 5 as a Markoff number. This is the maximum of the non-degenerated triplet. And you have 13, 29, and so on. You have many distinct Markoff numbers. And the Frobenius conjecture is just this. You have to prove that each Markoff number is the maximum of a unique triple. So if a maximum appears somewhere, it is unique in the tree. So it's really easy. You have a definition like this, okay, to generate all the triples. So, okay, but it's a very difficult conjecture. You have many good mathematicians that are working on this conjecture, but it's still unsolved. Okay, let's try to use combinatorics and try to go further. Oh, I like very much. In fact, on the left, you can see Fibonacci numbers, not all Fibonacci numbers. And on the right, you can see pale numbers. Okay, let's try. So here, you can see that we have, in fact, I think it's odd Fibonacci numbers, which are the maximum of the triplets. And okay, we can prove this, and in the other. So on the right, you have pale numbers. So the recurrence is Pn plus 1 equal to Pn plus Pn minus 1. And okay, the initial value are 0 and 1. And you can see that we have also odd pale numbers. And in fact, it's not so easy to prove that if you take the set of odd Fibonacci numbers and the set of odd, if in fact it's not odd, it's Fibonacci with a rank which is odd. Okay, so if you take the set of f 2n plus 1 and the set of p 2n plus 1, and to show that the only intersection is value 5, it's quite difficult article with Vuillon, Rothenauer, and Scienze. And they are using number theory in order to prove this fact. So it's not a good idea to look at the recurrence like this. Maybe it's better to put more structure and try to manage something. So let's start. So this is one article with Christophe Rothenauer in Montreal, and we use combinatorics. So it's combinatorics on words. So I shift I'm going to this topic. Here you have words in a two-letter alphabet. For example, here you have AABB, it's a word and the alphabet AB. And we can define the prefix of the word, so it's the beginning of the word. You can define the reversal, so you have a word and you look at the, so written with the letters W1, W2, Wn, and the reversal is just you look at the word in the other direction, so it's Wn, Wn minus 1 till W1, and you have a palindrome if W equal W tilde. Okay, it's really usual. So ABA is a palindrome, but AB is just a prefix of W. Now we are using the palindromic closure from De Luca, who was in Napoli, and he's working on combinatorics on words. So if you take a word X, you try to extend the word in order to find a palindrome. So you have to state the shortest palindrome having X as prefix. Okay, let's try. And we denote this by X plus in parentheses. Okay, let's try. So if you take A, it's a palindrome, so X plus is exactly A. Okay. If you take AB, then you put the center of symmetry on the B, and you have the shortest palindrome, which is ABA. Okay, and in fact, you can prove that X plus has the form X prime Y X prime tilde, so the reverse, if Y is the longest palindrome of a suffix of X. Okay. So here, so at the end, you are looking at the word, you are looking at the end, and you try to find the longest palindrome at the end of X. Okay. And this is why for AB, the longest palindrome is B at the end of AB. And so we use B as a center of symmetry. Okay, and now we are looking at iterated palindromic closure. So we are trying to make the closure many times. And we use here the iterated palindromic closure. So we use a directed word, which is D, and we can write D1, D2, Dn with Di are letters, and then the palindromic closure of D1, D2, Dn is a palindromic closure of the same word with you remove the last letter, palindromic closure of D1, D2, Dn minus 1. You add the last letter outside of the palindrome, palindromic closure, and you take the plus operator. Okay, so it's quite difficult at the beginning, but in fact, you will see that it's really natural. Palindromic closure of the empty word is the empty word. And palindromic closure of a letter is exactly the letter. Okay? So if you want to compute the palindromic closure of ABA, be careful. We have to compute the palindromic closure of AB and the palindromic closure of A. Okay? And so the palindromic closure of A is A, okay, because it's a palindrome. Palindromic closure of AB is, okay, I remove the last B, I make the palindromic closure of the beginning, so of A, I put the letter B of the directed sequence, in fact, and I compute the closure, okay, the palindromic closure. Mm-hmm. So you know that pal of A is A, so it's just the closure of AB. So palindromic closure of AB, we have already computed this is ABA. So now to compute palindromic closure of ABA, I put palindromic closure of AB, which is ABA, the last letter of the directed word, and now I have to compute ABAA in palindromic closure. So the center of symmetry is on the two last A, and then so I add the reverse of the beginning, so it's AB, AA, BA. Okay, so it's more convenient, in fact, to look at, okay, I can write it. You have a directed sequence like this. So it's A, B, A, okay? So I put the third letter of the directed sequence. It's a palindrome. So I do nothing. I put now the second letter of the directed sequence. So I make a palindrome here. So I put the center of symmetry on the B. And I put the last letter of the directed sequence here. And then here you have the longest palindromic suffix. So the center of symmetry is here. So this is the construction. It's better to look like this. Here you have a directed sequence. You use all the elements at the end of the previous word, and you compute this. And you can see that here there is a palindrome of length 1, and here a palindrome of length 3, but I add 2 letters, and here I had 3 letters, and so on. So this is the length of the what I add in order to construct the palindrome. Okay, we will see this. So now it's easy. For example, if you take this A, B, A, so I put the first A, it's a palindrome. A is a palindrome. Here I put the center of symmetry, so it's A. At the end, I put another A. So this is the center of symmetry. So you have something like that. So I put, you can see here, I underline the letters which are used from the directed sequence. Okay, and you can go further like this. So it's a method in computer science in order to construct. This is a part of Sturmian words. They are approximation of lines or segments. So it's quite natural. And this is the strange theorem with Rottenauer. We can look at the length of the Markoff of a word. Oh, okay. We construct the word like we take pal of AV or so you have a letter and V is a word. You have the palindromic closure. And you take theta. Theta is just the two-Morse sequence. So you have A goes to AB and B goes to BA. So this is a transformation. And then you use another time the palindromic closure. And if you are looking at the length of this, plus 2, it's a Markoff number. So it's really strange because you have this kind of palindromic closure. It came from theoretical computer science. And we are here in a real number theory when we are able to describe Markoff number by some lengths of words. And if you don't like this, the plus 2 in fact is like this. This is a palindrome in fact. And there exists a nice, if we put at the beginning A and B at the end of this palindrome, this is a Christoffel word. So we will see that it's a really approximation of a segment. And this special Christoffel words have exactly the length which are Markoff numbers. Okay. And maybe if we are able to look carefully at the structure of these words, so maybe we can learn something more on the Markoff number and the Frobenius conjecture. And the Frobenius conjecture is just to prove that each length, it's impossible to find two lengths that are the same in this set of words. Okay, so surjectivity is easy, but injectivity is equivalent to the Frobenius conjecture. So, let's try. For example, how to find the first Markoff number. You have the triplet, which is 1 to 5, so the maximum is 5. We will try to construct 5. So here we take V equal the empty word. So pal of A, we write AV just to break the symmetry in the word. We would like to have more A than B in the word. So in the pal of AV, just to break the symmetry. Okay. And okay, so if V is the empty word, so we can define palindromic closure of A is A. We take theta of A, it's AB, and we take the palindromic closure of AB, iterated, so it's A, B, A. Okay, it's a word of length 3 plus 2, we have 5. Okay, good. And we can go further. If we take V equal A, then it means that pal of AA is AA, okay? Just another. We put theta of this, so it's AB, AB, okay? A goes to AB, the second A goes to AB. And now we try to compute this. So look, at the beginning, we have a pal of AB, AB. So I put a A, so it's good, it's palindrome, then a B, so the center of symmetry is here. Then a A, center of symmetry is here. And then a B, we are looking here, this is the palindrome, PAB, and this is the longest palindrome, right? So the center of symmetry is here, you put. And if you compute the length, it's 11 plus 2. So you have a
curiosity, given the Markov number, there's an algorithm to find a word so that you get etc. plus 2 equal to that Markov number, or is it difficult to hear?
Okay.
Because the previous theorem says that it is surjective. But is the proof constructive or no?
In fact, we are able to find, given if you give me a Markov number, I can write the Markov number M as a P squared plus Q squared, the sum of two squares, and then I can write this morning. I can write some Markov words like this with exactly this, but there is no unicity at the moment.
So there is an algorithm.
Yes.
Okay.
Yes. We can guess, in fact, what is exactly the word. Surely, but we have to work to prove this. And what is interesting here is that if you take a V equal A to the power N, you recover all the Fibonacci numbers, in fact. So Markov numbers that are Fibonacci. And this is quite amazing. In fact, here you add, this is you add a word of length 2, here a word of length 3, and here a word of length 5, and so on. So you have the Fibonacci numbers appearing here, and you can compute it. And it's quite amazing. Now, if you want to find pale numbers, you take just V equal B. So here it's Fibonacci numbers. And if you take V equal B, so there is okay, so you are computing pal of AB, it's ABA. So you take theta, and so you have AB, BA, AB. Okay, and now we have to compute, and this is quite difficult. Okay, so we have ABA as pal of AB. Okay, we take theta of this. So, in fact, theta is just you instead of writing A, you write AB, and instead of writing B, you write BA. So theta is just something which takes the word and puts the same number of A and B. And then you compute pal of this. And it's quite difficult, but you can manage it. So you have A, B, put a B. Here, for example, the center of symmetry is here. So you put the A, so the center of symmetry is here, and so on. So here the growth is, where is it? The center of symmetry is here. So you add B, A, B, A, and the last B. This is your palindrome suffix. So you take this and you put here. So it's A, B, and so on. A, B, A. And you can see that here we have 1. We add a word of length 2. Here a word of length 2. Here a word of length 5. Here a word of length 5. And then here a word of length 12. Okay. And at the end, you find how many? 27, the length, plus 2 is 29. This is a pen number. Okay. And in fact, it's really related to Christoffel words. So you take a segment with from 00 to PQ, and you want to have a P and Q which are relatively prime. So you can define your Christoffel word as an approximation of your segment. And here you take the broken line, which is the closest to the segment, below the segment. And as you can see, that the beginning is A, the end is B, and here you have a palindrome. Okay, you have A, B, A, B, A, B, A, B, A. It's a palindrome. And in fact, the special Christoffel words with the palindromes is exactly given by this. And it's strongly related to Markov numbers. So now, I like very much to add the length of the word like this, because it's not so far from using here the Fibonacci rule, or here the Pell rule, because 5 is just the sum of the 3 last values, and 12 is just the sum of the 3 last values. Okay, so you have so we are able to explain this. So now we are looking at the directed sequence, which is now it's theta pal AV. This is a directed sequence. So this is the first element. Here, for example, we have the directed sequence, and we add a new palindromic closure. So we already done the theta pal AV process. So imagine that D is a sequence of letters with A and B. Okay, And we are able to define a linear recurrence associated with the construction of Markov numbers. This is quite interesting because, okay, if we have we are computing LG, and if in the directed sequence dg equal dg minus 1, so we just put LG minus 1. So it's exactly the case here. So here you have double B or double A, and here you have 2 times the same value and 2 times the same value. Okay. If we have a DG different from DG minus 1, different from DG minus 2, we are using a Fibonacci rule. Okay, here, for example, here you have A, B, A, B. So it's you have this characteristic. If there is no double consecutive letters, so we are using Fibonacci. If you have 2 consecutive letters that are the same, we are using a Fibonacci rule. So we are looking at the 3 last value, and we are making the sum. And that's all. So in fact, in order to construct the Markov numbers, we look at Fibonacci or at Fibonacci. But as we have the same value here for the consecutive letter which are the same, the Fibonacci rule is in fact a Pell rule, because okay, we have 2 times, twice the same value. And the length of your Markov word is just the length of the LE. The LE is exactly what I have put here. So when you are making the palindromic closure, you add at the end a part, some letters in order to make a palindrome. So the LE are exactly what you add at each step. And so we are able to compute easily for the empty word. Okay, for if we take now, so V is the theta of phi of AB. So if V is the empty word, we take theta of pi A. Okay. So it's AB. And you can, instead of making all this stuff, you use the recurrence in order to go faster. And you have many examples. So here, for example, if you take DA, it means that you are looking at D of theta pi of AA. So the directed sequence is okay, AB, AB. Okay, you have AA, and you take theta. And now the idea is to look at your directed sequence, and you can, this is the beginning. So you have 1, 1. The next value, 2 also. Here you have A, which is different from B, which is different from A. So you use a Fibonacci rule. Here you have a B, which is different from A, which is different from B. So you use another time the Fibonacci rule. Okay? And you are, in fact, you are computing exactly this. So you have 1 plus 2 plus 3 plus 5. So you recover. And you can go further. If you take always A like this, you can find Fibonacci numbers. And what is interesting also is this property. Here you have your sequence, but to find, I don't know if you are able to see this. So, okay, how to define, to find directly 34, how to do this? If you look at the two last values of your sequence, you can build 34. If you take 2 times the last value plus 1 time the other value, it's exactly 34. So you have a nice property in the LEs. It's the sum of the LEs, but this is also 2 times the last value, the last LEs, G and plus LG minus 1. So it's incredible. You have such kind of elements. Here for 29, we can define exactly the same construction. Okay. So here we have theta phi of A, B. Phi of AB is ABA. And this is AB, BA, AB. Okay. You have your image like this. And then you can write this and compute directly. So you have 1, 1, 2. Here you use, you have the same letter here and here. So now, for this value, you make the sum of the 3 last values. Here, this is you have the same letter, so you rewrite the value. Here, you use Fibonacci and so on. And then you can make so if you make the sum of this, you add 1, it's 29. Or you take 2 times this, plus 5 is also 29. Okay. But, okay, you can find Pell number or Fibonacci number. And here you mix the 2 elements. So, for example, if you take pile of AB, so pile of this is A, B, okay, it's this. So now it's AB, AB, BA, AB, AB. Okay, so this is your data. And you put 1, 2. Here it's a Fibonacci rule. Here you double the value. Here it's a Pell rule or Fibonacci rule. You double the value. Here you make the sum of the 3 last elements, so it's 21. And now it's a Fibonacci rule. So it's
31. Yes.
Oh,
in the slides.
There is something wrong in my computation.
No, the slides are correct, but
oh, it's 31. Oh, it's better, I guess.
In the slides, right?
It's better to read the slides. And so here it's associated with a Markov value 194. So we construct, in fact, a word of length 124. Okay. So this is the first part of the lecture. And what is interesting also is to prove that there is two rows. One is a Fibonacci rule, the other is a Fibonacci rule. And we have to prove that if we have a word with a certain length, there is a unique way. I think that behind this, there is a non-uniform numeration systems. Because here we are looking at a numeration system between Fibonacci and Pell. We are mixing the two. And the idea is try to find some elements either on the words or on the numeration system or on this construction with a linear recurrence. So this is the first part. Maybe I can explain the second part really quickly. So the real challenge is to prove that the words pal, theta, pal, AV have pairwise distinct lengths. And this is exactly the Frobenius conjecture. So we have exactly the object. It's really constructive, but it's difficult. With Edita Pelantova in Prague and my colleague in Chambéry, Clément Laguisquet and Sébastien Tabnas. So the idea is to prove three conjectures of on the book of Igner. So this is your tree, and this is another tree that maybe we're really familiar with, the Sternbroker tree. And in fact, there is exactly the bijection between the triplets and the Sternbroker tree. So here, for example, the triplet 1, 5, 2 is associated with 1/2. And you have it gives rise to two elements, 1/3 and 2/3, and it's associated with the two triplets here, and so on. So we are able to put a label on each triplet. And it's not only a label, it's also where the segment that we are discretizing in order to find the triplets. So it's really interesting. And so we can call M 1/2 is the Markov number 5, and so on. So you can associate a Markov to a Markov number a ratio like this, P over. And this is Igner's conjecture. You have a fixed numerator conjecture. If you fix the numerator, if you fix P, then you have this monotonicity. MP over Q is less than MP over Q plus I. If you fix the denominator, you have also monotonicity. So you fix Q and you have MP over Q is less than MP plus I over Q. And if you have the sum, which is fixed, there is also monotonicity. So it's quite interesting. And okay, we find there is this proof of the first conjecture by Rabideau and Schiffer, but it's quite technical and it's perfect matching on the snake graphs. So it's, you have algebra behind a snake graph, but it's quite difficult to read, but for me. So this is why we transform this on combinatorics. We have these con matrices, you have a product of matrices, and now we are making the product of matrices directed by a word. And if you are looking at the upper right element of your matrices, it's the valuation of Markoff of the word. And in fact, we find that, the valuation of Markoff of the Christoffel word here is exactly the length of this word. So there is a strong connection between the product of matrices. Of course, it's continuous fraction and expansion, but with another point of view. And we can extend also the valuation for such kind of the power of Christoffel words. Because in the Egner first conjecture, they are looking only with a PQ, which are co-prime. And this is the valuation of all the value on these two. In red, you find exactly the Markoff numbers, and we can extend the black part. Okay. But in fact, we are able to make the monotonicity in a row, in columns, or in diagonal. So this is the idea. And just to go further, we have, it's like in geometry, you have local flips. Okay, to have monotonicity here, you have a word. At the middle, you have AB. And you take the two letters, you exchange it on BA, and you have such kind of monotonicity. Sometimes it's in the one sense, and sometimes in the other. But
can you go back to the definition of M open parentheses? That is the
M is just this. You have
multiply for so essentially you are studying what happens when you swap two matrices in a product.
Exactly.
But the product, of course, is not commutative, so that's the
yes. This is a difficulty. Here we have only a local flip, but we would like to go, for example, from AABB to BBAA and find some monotone steps. But sometimes you have equality. Well, it's not a problem. But it's a problem here, because sometimes you have to flip many letters at the same time. Otherwise, you don't. It's impossible to have monicity here, because so you have to consider flip with in your product of matrix at the same time. But we are able to manage this, with we have a packed set, so you have your elements packed on the lower right part, like this. And if you have a segment, you have a flattening. So you remove the part which is in the upper part of your segment. This is a flattening. And we can prove that the Markov valuation of flat of W is always less or equal than the Markov valuation of W. Okay, and we have exactly the equality when flat of W is W. Okay, so W is a word, in fact, that are constructing this part. So you associate with A is a horizontal step, B is a vertical step. And the idea of the proofs, if if you want to go from this part to this part, so you move. So here you are exactly your word, and you remove the last B. And in fact, you have you make the flattening on the 3 elements, and you make it, you generalize this, and you are able to prove that monotonicity. And okay, we are able to find some optimality for Christoffel words. And so now this is the last slide. Here you have your Markoff valuation of P over Q. Here we are sure that all the Markoff numbers are less. Here we are sure that all the Markoff numbers are greater than N P over Q. And we have maybe some troubles for the Frobenius lecture here and here. So we have to go further. But okay, in the first part of the lecture, we managed to use combinatorics on words. Here, it's more on local flips on pass on Z2, but in fact, it's local flip on the product of matrices. And okay, the two methods are interesting, but we are far from the conjecture. But maybe you have some new ideas. So thank you very much.
Thank you.